welcome to Play-by-Play Regents Chemistry Take an Exam Day. Today we're going to do the June 24th, 2014 Regents exam. Now, the first part of this is going to be Part A, which is the multiple choice section. Then I'll do another video on Part B1, another multiple choice section, and then B2, which is a short answer section, and then Part C, which is yet another short answer section. Breaking it up like this, that you don't have to sit through the whole Regents exam. You can just take a look at the part that you want to take a look at. Now, the reason I'm doing this is because it's important to know the strategies of taking the exam. I mean, I can go over this exam all I want, but I'm going to try something new here today. I want to show you the thought process that goes into taking the exam, so that when you look at the question, you ask yourself, do I have enough information here? Is there a vocabulary term that's going to help me to solve this? Is there a reference table I need to go to? So I'm going to take you through the process of actually taking this Regents exam in chemistry. So let's start off with Part A. Part A of the Chemistry Regents exam is typically 30 multiple choice questions. And these questions are very heavy on vocabulary and making use of reference tables. If you know your vocabulary, Part A is going to be excellent. So as we go through, we're going to take a look at the vocabulary words that are important in answering each of the questions. Shall we begin? Let's start off with question number 1. Question number 1 says, compared to the charge of a proton, the charge of an electron has, well, there's no reason to guess. There's a reference table for that. If you want to compare the charge of any subatomic particles, the reference table that you should go to is reference table O. Now here on reference table O, you will see that a proton has a charge that is +1. The bottom number is the nuclear charge, or the charge of the particle. It can also be determined as the atomic number. So the question says, to compare to the charge of a proton, the charge of an electron has. Well, compared to the charge of a proton, which is +1, the charge of an electron is -1. Okay, so it's exactly the same magnitude, the same size, but it's the opposite charge. +1 in the case of a proton, -1 in the case of an electron. So compared to the charge of a proton, the charge of an electron has the same magnitude. There's two different choices. It comes down to 3 or 4. And the same sign? Nope, the opposite sign. Choice 4. You see how the question has two parts. It has the first half and the second half, and it's often easy to narrow it down to two choices. It has greater magnitude or the same magnitude. Well, we can eliminate the ones with greater magnitude, so we don't have to worry about that. So that's question number 1. Question number 2. Which atom has the largest atomic radius? Well, how the heck are we supposed to know? Fortunately, there's a reference table for that. And that reference table is reference table S. This is reference table S. It has a list of all of the elements by symbol and atomic number and name, first ionization energy, electronegativity, melting point, boiling point, density, and yes, atomic radius. So what we should do while we're answering this question is to look up the atomic radius of potassium, rubidium, francium, and cesium. So let's see, potassium, which is K. Here's potassium here. And potassium has, let me just get this into the, there we go. Potassium has a radius of 200 picometers, so I'll just write that down here, 200. And rubidium has a radius of, let's see, where's my rubidium at? There we go, rubidium is 215, so we'll write down 215. Now, so far it says largest atomic radius, so we can already eliminate potassium because rubidium is bigger than it is. Francium, let's way the heck down here. Francium has a radius of 242. 242. Let's see, 215, 242. Looks like rubidium's out and francium is our contender. And finally, cesium. Cesium here, cesium here. And that radius is 238. Let's move that over there, 238. For cesium, 238. Well, again, francium being 242 still wins. So choice 3, francium. Isn't this fun? By the way, today I am using my writing utensil. Yeah. Okay, next up, question number 3. There we go. Okay, the wave mechanical model of the atom. An orbital is defined as, okay, so now we're talking about definitions. Very rarely are they going to ask you for the definition of a word. Instead, they'll basically give you a question where if you don't know the definition, you can't answer the question. But here they're asking for a definition. The definition of an orbital is a region of space where you're most likely to find an electron, a region of the most probable electron location. That right there is the definition of the word orbital. Now, on the Regents exam, you'll need to know principal energy levels, or shells, as the most general location to find an electron, and the orbital as the most specific probable location. Now, that's the cool thing about electrons. There's just no way of knowing where they are, but you can know the general location in which you might find it. And these orbitals are shapes that represent space around the nucleus where the electron is most likely to be found. Okay, let's move on to question number 4. Question number 4 reads, when an excited electron in an atom moves to the ground state, the electron, okay, so we have an electron in the excited state. Now, that means that the electron is higher up in energy level than it normally would be. So, in other words, it's high, not low. So, an atom moves to the ground state. Well, let's see. In the excited state, it's got more energy. In the ground state, it has less energy. So, when it goes from the excited to the ground, when it goes down in energy level, it doesn't absorb energy, it emits energy. Okay, so that leaves us choice 3 or 4. Now, in the excited state, it's in a higher energy level. In the ground state, it's in a lower energy level. So it moves to a lower energy state. Choice 4. Question number 5. Which polyatomic ion is found in the compound represented by the formula NaHCO3? Fortunately, there's a reference table for that. And that reference table is reference table E, the table of the polyatomic ions. Let me get it in view here. Okay, there we go. Now, you'll notice that we have in our question NaHCO3. Now, do any of those appear on this table? HCO3 appears on this table. HCO3 is the hydrogen carbonate ion. And that leaves Na as the other ion. So this compound is made of sodium and hydrogen carbonate. The name of the compound is sodium hydrogen carbonate. And the hydrogen carbonate ion is the one we've identified. Thank you very much, reference table E. Question number 6 reads, the atomic mass of magnesium is the weighted average of the atomic masses of. Now, weighted averages. I do a lab in my class called the weighted average mass of paperclipium, which if you're one of my students watching this, you should remember. But the weighted average mass is essentially the weighted average of all of the naturally occurring isotopes of magnesium. So there's a vocabulary term for you. The weighted average atomic mass is the average of the masses of all of the naturally occurring isotopes for that element. Number 7. Which element has atoms that can form halide ions? Now, there are many groups on the periodic table. And each of those groups, many of them have names. For example, the elements in group 1 are called alkali metals. The elements in group 2 are called alkaline earth metals. The ones in the middle are your transition metals, the ones that form colored compounds. Your halogens are group 17. They include fluorine, chlorine, bromine, iodine, and astatine. These are your halogens, and they form halides. Chlorine, chloride, bromide, iodide. Those are your halides. So there's a couple of places you can get this information from. You can even get it from the organic chemistry reference table. Check it out. What do we got here? Halides. Fluorine, chlorine, bromine, and iodine. So what we're looking for is one of the halogens to be a halide. So is it iodine? Is it silver? Is it strontium or xenon? Well, it's pretty clear that iodine is a halide. So that's your halide right there. Iodine. Number 8. Two forms of solid carbon, diamond and graphite, differ in their physical properties due to the differences in there. Well, we're talking about carbon, and carbon has an atomic number of 6. That means it has 6 protons. With a configuration of 2-4, it has 6 electrons. So it has the same number of protons, the same atomic number, the same number of electrons. What can it differ in? Crystal structure. Diamond is a network solid, where you've got a network of bonds that go off in 3 dimensions. I really can't draw it here, but diamond is a network, whereas graphite is made up of thin sheets that are just weakly attracted to each other, whereas in diamond, these are actual bonds that hold it together. These are called allotropes of each other. Allotropes. A-L-L-O-T-R-O-P-E. They're the molecular forms of the same element, and the only difference between them is their molecular or crystal structure. Number 9. Which quantity can be calculated for a solid compound given only the formula of the compound and the periodic table of the elements? So we're given the formula of the compound and the periodic table. Now, can we get the density from that? Well, density equals mass over volume. And that's not information that we're given here, so no, it is not density. 2, the heat of fusion of the compound. Well, heat of fusion is defined as how much energy it takes to melt a substance. And we can find that information on the reference table. The heat of fusion of water can be found on reference table B. But that's not the periodic table. So, no, not heat of fusion. The melting point of each element. Well, let's see. The melting point can be obtained from reference table S. Yeah, that's not the periodic table either. So why is it choice 4? I mean, obviously it's the only choice that remains, but why the percent composition by mass of each element in the compound? So we have the formula of the compound. Let's say, for example, H2O, and the periodic table of the elements. Well, it turns out that percent composition by mass is equal to the mass of the part, which would be the formula mass of the element in question, divided by the formula mass of the entire compound times 100. And what can you find on the periodic table? Well, let's see. You can find the weight average atomic mass for every element. So based on atomic masses, we can find the percent composition of each element in the compound. Choice 4. Question number 10. Which terms identify types of chemical reactions? Well, let's just take each term in turn. Decomposition is when you take a compound and break it up into its individual elements. Now that would be a chemical change. So decomposition is definitely a chemical change. So we'll highlight that. That's totally possible. Sublimation is a phase change from solid to gas. Now, phase changes are physical changes because they involve only changing how far apart the molecules are from each other. So, solid carbon dioxide can undergo sublimation to form carbon dioxide gas, but it's still carbon dioxide. Sublimation is not a chemical change. So choice 1 is out. Choice 2, decomposition and synthesis. Well, we've already said that decomposition is a chemical change, where a compound decomposes into the elements that it's made of. What's synthesis? Synthesis is the exact opposite. Synthesis is combining two elements to make a compound, which would also be an example of a chemical change. So what about the rest of the choices? Now that we've narrowed it down, choice 2 is the correct answer. Why deposition? Well, what's deposition? Deposition is just the opposite of sublimation. Sublimation is solid to gas, deposition is gas to solid. Therefore, those are physical changes because they're just changes in phase. And deposition, okay, that's a physical change. And synthesis, well, synthesis is a chemical change, but in this question, both terms have to identify chemical reactions. And choice 2, decomposition and synthesis, are the only two that do. Question 11. The greatest amount of energy released per gram of reactant occurs during the greatest amount of energy released per gram of reactants. Okay. There are 3 kinds of changes. There are physical changes. None of these are physical changes. They would include things like melting, boiling, dissolving, stuff like that. Physical changes involve the least amount of energy exchange. Chemical changes involve more. Redox reactions, such as synthesis or decomposition or single replacement, involve more energy being exchanged. Substitution is an organic chemical reaction, and neutralization is a reaction between acids and bases. So choice 1, 3, and 4 are all chemical changes. Is there anything that can give you more energy than a chemical change? Heck yeah, a nuclear change, like nuclear fission or nuclear fusion, where a little bit of mass is converted into a sick, huge amount of energy. The nuclear change will win every single time with the greatest amount of energy. Question number 12. Which element has atoms with the strongest attraction for electrons in a chemical bond? Attraction for electrons in a chemical bond. This is a definition of the word electronegativity. Now, there are ways to memorize the trends or to know that fluorine has an electronegativity of 4 and it will steal electrons from any other element on the periodic table. But, of course, when you're taking a Regents exam, you might not be, you might be in a little bit of stress and that little fact might skip your mind. Fortunately, there's a reference table that has all the information that we need on it. And that reference table is reference table S. Electronegativity. So we can compare the electronegativities of different, there's fluorine at 4.0, beats out everybody. Chlorine has an electronegativity of, let's see, where's chlorine? 3.2. So I'll just write that down here, 3.2. And nitrogen is 3.0, so I'll write that down here, 3.0. Fluorine 4.0, fluorine 4.0, and oxygen, where are you, oxygen? There you are, 3.4. By writing the numbers down on your test, you can directly compare your numbers and find out which one has the strongest attraction. Well, the strongest attraction would be the one with the highest electronegativity, because electronegativity is defined as an atom's attraction for electrons in a chemical bond. This is one of the reasons why noble gases do not have electronegativity listed. You'll notice, for example, that helium has no, helium has no electronegativity listed, and neither does neon, and neither does argon or any of the other noble gases, because noble gases already have a stable octet. They do not need to gain electrons in order to form a stable octet. So they have no attraction to electrons in a chemical bond because they don't form chemical bonds. Next up, number 13. Compared to the physical and chemical properties of the compound NO2, the compound N2O has, well, let's see. Our first compound is nitrogen dioxide, and our second compound is dinitrogen oxide. Here's a simple fact. If you can give it a different name, it's going to have different properties of every kind. It will have different physical properties. It'll have a different melting and boiling point. It'll have a different solubility. It'll have different products from the reactions that it undergoes. That last, of course, being the different chemical properties. So if the substances are different, their physical properties will be different and their chemical properties will be different. Number 14. Which phrase describes a molecule of CH4 in terms of molecular polarity and distribution of charge? Well, it comes down to remembering that distribution of charge directly determines the molecular polarity. A molecule with a symmetrical distribution of charge will be nonpolar, and an asymmetrical or non-symmetrical distribution of charge will be polar. Now, what about CH4? Well, let's sketch it. CH4 there we go. It looks like it's symmetrical in more than one direction. That means electrons are being pulled evenly towards each side of the molecule. No side of the molecule will become more positive, no side will become more negative. So as a result, this molecule has symmetrical distribution of charge. Now, is a symmetrical distribution of charge polar? Polar means there's oppositely charged poles. There aren't any. It's not polar. It's nonpolar. Equal pull in all directions gives you a nonpolar molecule. So, it's got a symmetrical distribution of charge, which means the molecule itself is nonpolar. It's my writing utensil. Number 15. Which sample of copper has atoms with the lowest average kinetic energy? Well, who cares if it's copper? Doesn't matter whether it's copper, it doesn't matter whether it's your kitten, it doesn't really matter. Atoms with the lowest average kinetic energy. Average kinetic energy is measured with temperature. Temperature is defined as the average kinetic energy of a system, which means that mass has nothing to do with it. Get rid of mass, it's just a distraction. The average kinetic energy is the temperature, and this is asking for the lowest temperature. Well, it looks like the lowest temperature here would be 15 degrees. Number 16. Which change results in the formation of different substances? Well, there are only two kinds of changes. Physical changes, which do not change what kind of substance you have, and chemical changes, which do change what kind of substance you have. Now, if you burn propane, I'll actually show you the reaction. It's on reference table I. Here's the reaction for the combustion of propane. C3H8 plus 5O2. Oh, look at that. We don't have C3H8 or O2 on the other side. We've got carbon dioxide and water vapor. This would be an example of a chemical change, where the identity of your substance is different from one side to the other. Melting is just a phase change. Deposition is just a phase change. And solidification is just a phase change. Solid to liquid for melting, gas to solid for deposition, And solidification is just a fancy word for freezing or liquid to solid. Any way you look at it, the substances do not change their identity. When you go up in phase, the molecules simply get further apart. When you go down in phase, the molecules just get closer together. But what molecules you have, that doesn't change. Question 17. Which substance cannot be broken down by chemical change? Well, that substance, of course, would have to be an element. Elements cannot be broken down any further by chemical change. Compounds can be decomposed into elements. In fact, the definition of a compound is two elements that are chemically combined, which can be decomposed back into those elements. Ammonia is NH3. That's a compound. It can be broken down into nitrogen and hydrogen. Which substance cannot be broken down? Not ammonia. Ethanol is ethyl alcohol, C2H5OH. That's definitely a compound. It can be broken down into carbon, hydrogen, and oxygen. Which substance cannot be broken down? Not ethanol. Propanol is an aldehyde, and once again, aldehydes are organic compounds, and compounds can be decomposed. However, zirconium is an element, and elements cannot be decomposed chemically any further. If you want to decompose a compound, you're going to have to go not to a chemical change, but to a nuclear change. And in this question, it says very specifically a chemical change. Our element cannot be broken down by a chemical change. 18. According to Table I, which equation represents a change resulting in the greatest quantity of energy released? It's very rare that they'll actually tell you what table to go to. Most of the time, the question will simply read, which equation represents a change resulting in the greatest quantity of energy released? And you look at the question, you'd be like, how on earth am I supposed to know that? There's no way by looking at these formulas that you can tell how much energy is absorbed or released, or whether it is absorbed or released. Here they tell you to go to Table I. Most of the time, they won't. Table I has a wealth of information, not the least being that on the bottom it says a minus sign indicates an exothermic reaction. So any change here with a negative delta H value, a negative heat of reaction, is going to be exothermic, and anything with a positive change in heat will be endothermic. Now this question says resulting in the greatest quantity of energy released. So we're looking for an exothermic reaction with the biggest possible number. So let's see. 2 carbons plus 3 hydrogens forms C2H6. C2H6. The formation of C2H6 releases 84.0 kilojoules. So this releases 84.0 kilojoules. 84.0. I'll write that down there. C2H4. The formation of C2H4, here we go, C2H4, that absorbs energy. We can eliminate that choice completely. Goodbye. Choice 3 forms NH3, the formation of ammonia. And the formation of ammonia releases 91.8 kilojoules. Negative 91.8. Well, that's greater than our 84, negative 84, so we can eliminate choice 1 as a possibility. The formation of NO, okay, absorbs energy. Well, we want releases energy, not absorbs energy, so we can get rid of choice 4. We have a winner. Ammonia releases the most energy according to Table I. And most of the time, they will not tell you to go to reference Table I. I'm telling you now, that's where you gotta go if you're talking about energy. Number 19. There are two elements on the periodic table that are liquids at STP, standard temperature and pressure, and they are bromine and mercury. Now you could memorize it. You know, bromine and mercury are the two liquids on the periodic table. The other way you can do it is to look it up. First of all, what is STP? Since melting point, which is what determines whether something is a liquid or not, is based on temperature, standard temperature is 273 Kelvin. 273 Kelvin. Which element is a liquid? Well, we want a liquid that has a melting point that's under 273. For example, if it melts at 250, then above that, like at 273, it's a liquid. And we also want the boiling point to be above 273. So let's go through the elements and figure it out. Fortunately, again, you do not need to guess. Reference table S. Reference table S will give you all the information about melting point that you need. And it turns out that bromine, our very first choice, has a melting point of 266 Kelvin and a boiling point of 332. 273 is in the middle. It's between melting and boiling. Hey, guess what, folks? That makes bromine a liquid. If you take a look at these other three choices, their melting points are all above 273, which means at 273, the other choices are all solids. Number 20, which statement describes a reversible reaction at equilibrium? At equilibrium. This is one of the most forgotten and misunderstood vocabulary definitions there are. Equilibrium is when the rate of a forward change, the rate, okay, not the amount, when the rate of the forward change equals the rate of the reverse change. Equilibrium is when the rate of the forward change equals the rate of the reverse change. Rate equal. None of the other choices work at all. Now, one other thing that they could give you here is they could give you a choice that says the concentrations are equal, which would be incorrect because equilibrium has nothing to do with equal concentrations. Or they could say the concentrations are constant. If the rate of the forward change equals the rate of the reverse change, that means over time the amounts of substance are not changing. They're being used up at the same rate you're making them, so that over time their concentrations remain constant. So equilibrium is a state at which the rate of the forward change equals the rate of the reverse change in a closed system, and under those conditions, concentrations will remain constant. Number 21. Given the balanced equation representing this reaction, what energy occurs during this reaction? Let's hold off on the energy business. Let's take a look at whether bonds are formed or broken. We start with a molecule, we end with individual atoms, and that means that bonds are broken. That means we can immediately eliminate choice 4, and we can immediately eliminate choice 2. There we go. Now, is energy absorbed or released when you break a bond? Well, if you think about a potential energy diagram, whether it's exothermic or endothermic, the first half of it is the activation energy. In order for a chemical reaction to take place, old bonds must break before new bonds can form. So the first half of a PE diagram is the breaking of old bonds. The second half is the forming of new bonds. So energy is absorbed to break bonds and released when new bonds are formed. So energy is absorbed as bonds are broken. We call that activation energy. Question 22. In terms of entropy and energy, energy, by the way, can also be called enthalpy. Forgive me, I'm writing on an angle here because of the way the camcorder is sitting, but in terms of entropy and energy, potential energy, systems in nature tend to undergo changes towards. Well, here's a nifty little fact. Nature is lazy and messy. Lazy and messy. Nature will always favor lower energy states. That's why an object at rest will remain at rest until you act upon it by an outside force. We call that inertia. So what happens is nature will favor lower overall energy. We can eliminate choice 4 and we can eliminate choice 2. What about entropy? Well, what is entropy? Entropy is a system's state of disorder, randomness, chaos, messiness. Now, be honest with yourself. Does your room get clean by itself, or does it get messy by itself? Of course it gets messy by itself. Things tend to go towards more disorder over time. So nature favors higher disorder, higher entropy. Higher entropy and lower energy. Nature is lazy and messy. Question 23. Which term is defined as the difference between the potential energy of the products and the potential energy of the reactants in a chemical reaction? Well, the definition is actually the definition of heat of reaction. The heat of reaction is the difference between where you start and where you end energy-wise. In a potential energy diagram, never go to the bottom. In a potential energy diagram, the heat of reaction, which is what we also call delta H, is you take the heat of the products and subtract the heat of the reactants. So let's say the heat of the products was 10 kilojoules, the heat of the reactants was 30 kilojoules. The heat of reaction would be 10 minus 30 is negative 20 kilojoules. Heat of fusion? No, that's the amount of heat it takes to melt a substance. Activation energy? No, that's the energy it takes to get to the top. Thermal energy? Well, that's just another word for heat. We need heat of reaction. 24. What is the atomic number of the element whose atoms bond to each other in chains, rings, and networks? Is the name of the element that allows you to create long chains of molecules, anything from alcohols to aldehydes and ketones and polymers. What do we call these? We call it carbon. Organic chemistry is the chemistry of carbon. Okay, well this says, what is the atomic number of that element? Well, the atomic number of that magical, amazing element carbon is, in fact, 6. So carbon is atomic number 6. There's no other element that can do what carbon does. Silicon can to a small degree, but not like carbon. There are over 7 million known compounds containing carbon, and that's because of all the various shapes that the molecules of carbon can take. What about network? That would be diamond, of course. 25. How many pairs of electrons are shared between two adjacent carbon atoms in a saturated hydrocarbon? There is a lot to unpack in that question. First of all, what is a saturated hydrocarbon? Reference table Q gives us our various hydrocarbon types. We have alkanes, alkenes, and alkynes. Now, for alkanes, if you want to put anything else on this molecule, you're going to have to pull a hydrogen off to do it, and that would be called a substitution reaction. This is a saturated hydrocarbon. Well, to understand why it's called saturated, I have to explain why these two are called unsaturated. If you want to put something else on this molecule, you don't have to remove hydrogens. You can simply break that double bond, and when you do, each carbon will have another bond that it can use to bond to something. So if we want to add more hydrogens to this molecule, we can break the double bond, and each carbon will be able to add an extra hydrogen to it. Because these can undergo addition reactions, because they have a double or triple bond, these are unsaturated. Because this can't break a double bond to add more to the molecule, this is saturated. So single bonds are saturated, double or triple bonds between carbons are unsaturated. So back to the question, which says, how many pairs of electrons are shared between two adjacent carbon atoms in a saturated hydrocarbon? Well, here would be your example of a saturated hydrocarbon, and here's the bond between the two carbons. Now, when electrons are shared, that's a covalent bond. And a covalent bond is defined as a pair of shared electrons. How many pairs of electrons? Since it's a single bond, one pair. An alkene would have two pairs, one for each bond, and the alkyne would have three pairs, one for each bond. 26. Given the balanced equation representing a reaction, 4 aluminum solid plus 3 oxygen gas forms 2 aluminum oxide solid. As the aluminum loses 12 moles of electrons, the oxygen, we don't even need to look at this equation. Who cares? The law of conservation of mass states that you cannot create mass, you cannot destroy mass. So if 12 electrons are lost, then 12 electrons will have to be gained. The law of conservation of mass says you cannot create mass and you cannot destroy it. So if the aluminum is losing 12 moles worth of electrons, those same 12 moles will have to be gained, in this case by the oxygen. Now choice 4 says loses 12. Well, the aluminum is doing the losing, which means that the other thing's going to have to do the gaining. "27. Which compound is an electrolyte?" Now here's another one that people will often have difficulty with. An electrolyte is a substance which, when dissolved in water, breaks up into ions, and those ions can carry electrical charge, which conduct electricity. And only 3 kinds of substances can act as electrolytes: acids, bases, and salts. So anything that's an acid, or a base, or an ionic compound, which is neither an acid nor a base, can conduct electricity. What cannot conduct electricity? Things that are covalently bonded, with the exception of acids. So how on earth are we supposed to know what we have? We've got 4 different kinds of organic compounds. We have an aldehyde, we have an ether, we have whatever this is, and we've got this alkane thing going on here. Well, let's see what's going on. Let's go to table K. Common acids. One of the forgotten tables. Oh, looky what we have here. I'll move this up so you can actually see it. C3COOH. They love putting this as the choice to this question because you see OH and you think base, which would still be an electrolyte, but that's not a base. This H right here, which would be that H right there, that's the one that comes off when you dissolve it in water. You'll notice bases are metallic hydroxides. Well, and then there's ammonia that's aqueous. CH3COOH. Why? Well, not only is it on reference table K, if you take a look at reference table R, you might notice that anything that ends in COOH is known as an organic what? Organic what? Acid. Organic acids can act as electrolytes. Weak electrolytes, but still electrolytes. Number 28. Which statement describes one acid-base theory? This kills me. There are two acid-base theories that the Regents tests. One of them is called the Arrhenius theory. Now, the Arrhenius theory is the one that states that an acid is the one that yields H plus when dissolved in water, the only positive ion in solution. And an Arrhenius definition of a base is anything that dissolves in water to yield OH minus as the only negative ion in solution. So what is this other theory they're talking about? It's called the Bronsted-Lowry theory, although they're not going to give it to you by name. Don't know why they don't call it the Bronsted-Lowry theory. They have no problem giving you the name Arrhenius, as you'll see in the next question. Why Bronsted-Lowry? They just call it one acid-base theory, which is way too vague. Anyway, this definition, the Bronsted-Lowry theory of acids and bases, defines acids as anything that gives up H+, an H+ donor. It's kind of like a kidney donor, but you don't need surgery for it. And if the acid is an H+ donor, then the base is, oh, this says H-. Why did I even choose that one? And the base is an H+ acceptor. This is merely the definition of Bronsted-Lowry acids and bases. Of course, they won't call it Bronsted-Lowry, they'll call it another theory of acids and bases. It drives me crazy that they do that. Anyway, next question is question 29. Which compounds are classified as Arrhenius? See, look, there it is, Arrhenius. They have no problem using the name Arrhenius, but they won't give you Bronsted-Lowry. No, they just say another theory or one acid. Anyway, that's my issue. Which compounds are classified as Arrhenius acids? Well, what if you don't remember that acids start with hydrogen? Well, unless it's an organic acid, in which case it ends in COOH. Even easier way to tell. Here's a table of common, look at that, a table of common acids. Well, look at all those acids. Acids like HCl. Oh, look at that, HCl. HCl. Yay. HCl. HBr would also fall into the same category, of course. HBO wouldn't. That's where you watch Game of Thrones. NaOH, is that an acid? No, NaOH is not an acid. Oh, look at that. NaOH is a base, so it's not NaOH. Sorry, buddy. HNO3, is that an acid? Oh, look at, there it is, HNO3. Yay. And NaCl, well, it doesn't have H or OH, that's just a salt. Go away. NH3, that's just a molecule. Now, we've got NH3 aqueous here, but it's listed as a base, not an acid. Sorry, you lose. We're looking for Arrhenius acids. H2CO3, well, it doesn't matter because if they're not both acids, then it can't possibly be the correct answer. Number 4, H2SO4, you better be an acid, otherwise we got a problem. Oh, thank goodness for that. Look at that. H2SO4 is one of the common acids. Awesome. HBr and H2SO4. Surprised they didn't throw in a CH3COOH too. They love CH3COOH for acids. And finally on part A, which statement describes the stability of the nuclei of potassium atoms? The stability of the nuclei. Well, there's two kinds of nuclei. Nuclei that are stable Stable nuclei will last pretty much forever. For example, every single atom of hydrogen with a mass of 1 or 2 that has ever formed in the universe has survived ever since it was formed. Every hydrogen atom in existence today has been in existence for the last almost 14 billion years. Now, of course, some hydrogen nuclei have been fused in the middles of stars, but those that haven't, those stable hydrogen atoms, those have been in existence since the beginning of the universe. Any heavier element that was formed by nuclear fusion or by the process of a supernova explosion, if the nuclei is stable, well, guess what? They've been around ever since then. Every stable atom on our planet has been in existence for more than 4.5 billion years. That's a stable nucleus. So what about unstable nuclei? Well, we call them radioactive. And for potassium, on table N, there are 2 isotopes of potassium that are listed that are radioactive. Now, are all potassium atoms radioactive? No. Until you get to element 83, every single element has both stable and unstable isotopes. Once you get to element 83, which is bismuth, it's the last one that has both stable and unstable isotopes. Once you get to polonium and everything after is only radioactive, unstable. And that does it for part A of this Regents exam. Stay tuned for part B1, coming up next.